So let me talk about the technologies that that I have used for the robot. So we have this robot. We have 6 wheels in here, and 4 of them are basically omni wheels. Those has like rollers on the wheels, so it can actually go straight, and it can also um, allow the robot to like rotate in place. And the the middle one, this one has a motor inside. This is a hub motor. So there are like two of them. So there are like two more hub motors, and to drive them we need a motor driver. So we need two of these motor driver. Uh, so one goes to one wheel and that goes to the other wheel, and this motor driver is connected to a computer that calculates the path, how to drive the robot, and then sends the signal to actually drive it. So these motors are three phase motors. So we need a special way of driving it. So it will be complicated to explain in this scope. So there are a lot of resources on the internet. So this is called brushless uh, DC motors, and then if you search for brushless DC motor controllers, there will be a lot of resources available. So to build these controllers, you can find it for like $15, and it can go to 150 and more based on what features we want. For this particular robot, pretty much the cheapest one should work, even though I have used a more expensive one for the first robot, because that was easier to test it and do bunch of things. But at the end, it should not cost more than say $10 if we build it in volume. All right, that's the motor driver, and then we need to actually understand the path where we'll be driving. So we have a map. So initially, what I did is I actually created the map because I wanted to do it fast. So even though creating a map sounds slower, but I need a map around the lab. So it's just like a few hundred meters around the lab, and then what I did, I have a GNSS receiver in here. It is most of the time it is called GPS receiver. So GPS antenna. So this GPS antenna is connected to a GPS receiver that is actually receiving the position, and then I'm just recording it inside one of these compute units. So I have actually 2 computers on board. So one of them is actually recording it. So there are also 3 cameras. So 1, 2, 3. These 3 cameras are connected to one of these compute units, and I am collecting the images from the camera and the global positioning systems. And this is actually called GNSS instead of GPS. GPS is US version of the GNSS, I believe. So anyway, I use those, both of these. I use GPS. This is easier. So GPS position and the camera, these 2 are recorded. And once I have that, I have a map, and then I also have how the like path looks. So, and then what we have is I have a Xbox controller that has a, so I use Xbox One controller that has a Bluetooth receiver. I mean, it doesn't have a Bluetooth receiver, but inside there is so it can connect to any Bluetooth receiver. So I bought a small Bluetooth receiver and connected to this one of this compute, and then these two can connect over Bluetooth. So I use this Xbox controller to actually drive it. So I get the signal from here, and then I calculate how much rotation the user wants, and then I take the value of the rotation on the joystick, and then apply it to the wheels. So we have two wheels that is not actually connected. So these two wheels can be driven independently with different speeds. So this combination is called differential drive. So I can rotate one wheel clockwise and another wheel anti-clockwise. So that way it can actually turn. Actually, it can turn right at where it doesn't have to go forward or backward. It can turn in place. So this is the differential drive system. And yeah, so I can rotate the robot. I can move the robot. So if I press the joystick forward, the robot moves forward. So I get all these values from the Xbox controller, and then calculate a little bit, and then push it through the BLDC motor driver. With this I can actually have a moving robot. And then what we have is, from these cameras I am getting images. So what I am doing is, I already have a mobile Android phone on this robot. So I can actually connect to this robot and see what are the images this robot is collecting in real time. So what I did, instead of doing that, I created a small WebRTC client. So WebRTC client that is connecting to a client on my desktop. So this is a desktop. This is actually a browser. It's inside a Firefox browser. So it is connecting through WebRTC to this browser over phone network, basically mobile phone network. So I have a Android phone on board this robot. So I can actually see what the robot itself is seeing. So there are like 3 cameras. I can look into any of these. I can actually look into all 3 simultaneously, and I can see where the robot is going, and then I can connect the Xbox controller with this desktop machine, and then over the data channel. So we have this media channel that is streaming the video, but over the data channel I can actually send the control signal from the Xbox, and the robot actually drives. So that's the basic setup for this one. It drives pretty well. I have driven 10 miles on a single trial. It lost a few nuts and bolts. They just gets loose for some reason. No matter how much I try to tighten this. So what I am doing now is I am drilling the bolts and putting some wires inside it and bending it, so those does not come out, but it happened in both of my drives. So it can drive pretty well. So the hardware is ready, and also I can control it like this is teleoperation basically. I can control it from my lab, from anywhere, wherever I have internet connection, and it just goes. Now what I need to do is I need to take these images and actually try to understand the path of the robot and drive it autonomously. These will probably take time. So everything I'm doing like mostly alone. There is no other person helping me at this moment. Doing this entire thing alone will probably be taking too much time. So what I'm planning is I'll be actually using this robot at this stage to deliver to some of the clients already. So I'll collect more and more of these images and positions. So for the position, this GPS has a technology called RTK. What it does, we have a base station here near the lab. I just put another antenna and another receiver, and then I can take and then I know the exact position of this fixed antenna because it is not moving, so it's relatively easy to get the exact position. And then from the exact position, and I can calculate the error of this GPS signals that is coming from the satellite. And then if I send that information to the robot can actually use that error numbers and precisely localize itself. So this is RTK. I have not built it. It is a standard thing, and there is a server. There is requirement of a server that is called like Entrip server. That's basically sending the information about the error. Everything is, you can just find it online and then install it. So I have installed it in one of these rooms and connecting it over the phone network to the robot. So that's how it is working, and that's actually pretty good. Most of the time, probably like 95% or more time, it's really like the error is less than 10 centimeters. So if the error is always 10 centimeter, we don't need anything. We could just depend on it, but it's not always like that. 5% of the time it loses signal. It does, like, it cannot calculate where it is, and so it also gives us like the confidence. Sometimes it's like really confident, but it's actually wrong. So it's hard to depend on it 100%. So that's why we need cameras and other sensors. So yeah, so I have this RTK base station here in one of these rooms, and yeah, I'm using it to get the position and then images. And from these images, I'm actually making this labeling these images for now. So I label it like this is a sidewalk, this is a street, this is a like tree, this is a home, things like that, and then train a neural network with this information. And then for a new image, I give it a new image and then ask it, now tell me what is what. So if it can accurately tell me this is the sidewalk, then that's good. And there are a lot of algorithms for that. This technology is called semantic segmentation. So if semantic segmentation works, it's really easy to actually drive most of the time. I still need to detect like people, other vehicles, smaller vehicles, maybe bicycles, cars, things like those. There are like detection algorithms as well. I'm working on those as well. So I'm using basically YOLO view. So YOLO view 4. That can actually run on a smaller not Raspberry Pi, but there's some nano type of device. I see one of my friend is actually doing object detection like car, humans, bicycles detection on Jetson Nano. So that's really good. So if we can do with really small amount of compute, and we can also do semantic segmentation in relatively small amount of compute, we don't need a lot of compute for the entire thing. So the compute requirements is basically 1 nano Jetson Nano, or maybe 1 Jetson NX, Xavier NX. That will be sufficient. So that is still I have to do, but in the meantime I'll start to actually deliver those packages.